This is electrostatics examples number 5 and 6. These will be the last two examples for this unit. This is a old TV. We call this a cathode ray tube, and essentially what it is there's an electron emitter in the back, produces electrons, and they go through this focusing unit, and then they are accelerated using these plates, and they are also deflected by those. That electron then travels on through, and then it will hit the spot on a phosphor-coated screen, and it will either light up, in this case it's either going to be a white spot or a dark spot, because it's a black and white TV. So these are definitely different than your LED or LCD or plasma TVs. It tells us that there's an electron that's accelerated, so we know that the charge on an electron is 1.6 times 10 to the negative 19th coulombs, and they also tell us that the voltage in the system is 22,000 volts. Because that voltage is so high, that's why they tell you on the back of a lot of TV sets not to open them for fear that you might become electrocuted. If we want to find in this problem the kinetic energy that is lost by this electron as it travels from the back focusing unit up to the screen. And if we remember, work is actually equal to the change in energy. If I want something to start at rest and then move so that it picks up a really high speed, so let's just say 100 meters per second, and it starts at 0 meters per second, I have to do some sort of work to get that to happen. So now we can say work is equal to the change in energy. And for this problem, we're going to say work is equal to the change in kinetic energy. They want to know how much work it takes. So the equation we can use is the voltage, or potential difference, is equal to the work divided by the charge. And because we're looking for work, we're going to rearrange the equation. We're going to say work is equal to voltage times that charge. Our voltage is 22,000 volts, and we know the charge is 1.6 times 10 to the negative 19th coulombs. If you multiply those two numbers together, you should end up with 3.5 times 10 to the negative 15th. And remember, because work and energy are in the same units, we'll displace a joule in that spot. And that's the end of number 5. Let's go on to number 6. In number 6, it says Amir shuffles his feet across the living room rug. He builds up a charge on his body. A spark will jump when there's a potential difference of about 9,000 volts between the door and Amir's hand. So we know that the potential difference in this picture needs to be about 9,000 volts before that spark is actually lights up Amir's hand. It says that it happens when his hand is 0.3 centimeters, so I know this distance is 0.3 centimeters from the end of his finger over to where the door is, and so it's actually that little distance there. Remember, we can't have anything in centimeters. We need to make sure everything is in meters, and so if I divide this by 100 centimeters in a meter, I end up with 0.003 meters. Now I have a distance, d, and I have a voltage, v, so all I want to do is find out what is the electric field. The electric field is here, so here's our E. Voltage is equal to electric field times the distance that electric field acts, and our voltage is 9,000 volts. That's equal to the thing we're looking for, which is electric field, times the distance that it acts over, which is 0.003 meters. So now I'm just going to have E is equal to 9,000 divided by 0.003, and we see that this is a pretty large field. It's about 3 times 10 to the 6th volts per meter is the unit. And that would be the end of the example problems for electrostatics.